Hello students, this is Mr. Allen, and today we're going to look at section 9.4 and 9.5, and yes, I have a mustache today. So yesterday was Pi Day, and there was a famous TV show from the 1980s called Magnum P.I., so P.I. like pie. So in honor of Tom Selleck, I am rocking a mustache. So we're going to try to look at polar coordinates, and we want to be able to write rectangular coordinates and equations in polar form and vice versa. We want to be able to find the slopes of tangent lines, so that's going to be the derivative. We want to find area of regions in a polar graph, so that's going to be integration. And of course, arc length. So far, we've been representing our graphs as a collection of points x, y in the rectangular coordinate system. The corresponding equations for these graphs have been either rectangular or parametric form. So that's the form we've always used. Both parametric and rectangular are using rectangular coordinate systems. In this section, we are going to study coordinates called polar coordinates, which I'm sure you're familiar with from pre-calculus. To form a polar coordinate system in the plane, we fix a point O called the pole or the origin and construct from O an initial ray called the polar axis. So in this picture here, you can see that we have the pole at the origin, and then we have the polar axis, which in this case is kind of the x-axis, if you will. Then each point P in the plane can be assigned a polar coordinate, r theta, where r is the directed distance from O to P, and theta is the directed angle, clockwise from the polar axis to the segment. So in our previous example here, we can see that this point P appears to be in the first quadrant. We could, instead of calling it XY coordinates, we could say that R is some distance from the origin, and then theta is that amount of angular rotation from the polar axis. So if we look down here at the bottom, we see three examples. So looking at the first example, we can see that the point 2 pi over 3, that means the distance from the origin to the point is 2, and then the measure of the angle is pi over 3. Notice that in this system, it's convenient to locate points with respect to a grid of concentric circles inscribed by the radial lines through the pole. With rectangular coordinates, each point xy has a unique representation. This is not true for the polar coordinate system. So for example, r theta and r comma 2 pi plus theta will be the same point. Okay, so in other words, if we go back to, let's say, this first example A, 2 pi over 3, well, 2 and then comma 2 pi plus pi over 3, that's just going to take you another full rotation around and you will end up in the same place. You could also do negative representations. If you look at the third example there, we could say that that is 3 11 pi over 6, or you could even call it 3 and the negative 1 pi over 6. To establish the relationship between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis and the pole with the origin. Because x, y lie in the circle of the radius r, it follows that r squared is equal to x squared plus y squared. Moreover, for r greater than 0, the definitions of the trigonometric functions imply that tangent theta is y over x, cosine is x over r, and sine theta is y over r. And so that leads us to our conversion formulas for polar coordinates. So if we want to go from polar to rectangular form, we would use these formulas on the left. So in other words, if I said that x was 2, and let's say we knew that y was, I don't know, let's just say 3, then we could use, actually, let me pick some easier values here. Let's say x is 3 and y is 4, because those are going to satisfy the Pythagorean theorem a little bit easier. So we can convert those using our definition of rectangular or polar coordinates. So if we wanted to know what the x coordinate is going to be, to go from polar, I guess I'm doing this part here, aren't I? I'm sorry, I'm doing rectangular to polar. So if you want to convert the 0.34 to polar, Well, then you would just do tan theta. So you would do tan theta equals 4 over 3. In other words, theta would be equal to the arctan of 4 over 3. So that's how you can convert from rectangular to polar. Now, if you want to go from polar to rectangular, then we're going to use these formulas here on the left. So you would know what r is and you would know what theta is. So then to find x, so let's just say r is 1 and theta is, let's keep it super simple. Let's say it's pi over 4. You can plug those into this. In other words, 1 times the cosine of pi over 4, that'll tell you what x is. And then same thing for y. So let's do an example. So let's convert the point 2 pi into rectangular coordinates. Well, so here we know that we know that the radius is 2, and we know that theta is pi. So we're going to just use this formula here to convert it to the rectangular coordinate system, which is going to give us, in this case, -2. And then we're going to do the same thing for the y coordinate. So we're going to do r times sine theta. So that's going to be 2 times the sine of pi, which is 0. So that's 0. In other words, in the rectangular coordinate system, it's -2, 0. And here's another example. I'm actually going to skip this to keep the video a little bit shorter. But here again, we've got polar coordinates. And if we want to convert those to rectangular, we use the formula. And that's how you'll do that. Okay, so let's look at graphing polar equations. Let me tell you before I forget, with your graphing calculator, you can graph in polar coordinates. You just need to make sure that your mode is, instead of being in function, needs to be in polar. So we're going to look at 3 graphs here. We're going to look at A, where r is 2, B, where theta is pi over 3, and C, we've got r is equal to secant theta. All right, so the first one, which was r equals 2. So the radius is 2, if you will. The length from the origin to the point is 2. So that's just going to be the concentric circle with center of 0, 0 and radius of 2. So it's going to be the set of all points that are exactly 2 away from the origin. We can write this equation, just like I said, using the fact that it's a circle, so it's just going to be x squared plus y squared equals 4, which again is the equation of a circle with a center of 0, 0 and a radius of 2. B, now we're going to look at the graph of the polar equation, theta equals pi over 3. So this is all the points that have a radius, or not a radius, a theta of pi over 3. So the angular measure from the pole is going to be pi over 3. So this is going to be this diagonal. And if we want to convert this to our rectangular system, again, we're going to use our relationship right here. Tangent theta is equal to y over x. And so we're going to get y equals square root of 3 over x, because arctan of pi over 3 is radical 3. Finally, the graph of secant, or r equals secant theta. It's not evident by simple inspection. In other words, we probably need to do a conversion here. So we're going to use this relationship here. We know that x is equal to r times cosine theta. So in polar form, we got r equals secant theta. So we could divide both sides by secant theta. Or I'm sorry, we could divide both sides by cosine theta. And then, of course, secant theta over cosine theta is just going to be 1 on the right-hand side. And you're going to get r cosine theta equals 1. So x is going to be equal to 1. So again, this is tied to the formula for x, right? X is equal to r cosine theta. So x is 1. So this is going to just be a vertical line at x equals 1. But in polar form, that's what it looks like. So this is not intuitive. You need to be careful, and you need to go back and use these formulas on this slide right here. This is the big slide for converting from polar to rectangular and rectangular to polar. All right, so let's go ahead and move on. To find the slope of the tangent line of a polar graph, consider the differential function given by r equals f theta. To find the slope of the polar form, use the parametric equation. So now what we're going to do is we can convert our variables to parametric. We know that x is equal to r cosine theta. We know that y is r sine theta. So we can go ahead and convert that. Using the parametric form, this gives us dy dx, and this is theorem 9.7 from the last section. So we get this formula here, which establishes the following theorem. So here is the formula to find the slope of the tangent line, aka the derivative in polar coordinates. It is f theta cosine theta plus f prime theta sine theta divided by negative f theta sine theta plus f prime theta cosine theta. This is something that I would highly recommend that you put it on your list of things to memorize. Let's look at an example. We're going to find I'm going to do one example of these. This one's kind of an easy one. We're just going to do horizontal and vertical tangent lines because we know those slopes already. So it says find the horizontal and vertical tangent lines for r equals sine theta from 0 to pi. Okay, so first, let's go ahead again and write them in parametric form. That's why we did the parametric section before we did this. So remember, x is equal to r cosine theta. So that's going to be sine theta, because that's what r is, cosine theta. You can do the same thing with y, which is going to give us sine squared theta. Next, we're going to differentiate x and y with respect to theta for each derivative equal to 0. So we're looking for in this case, the horizontal tangent lines. So we're using this formula. And so the derivative of x with respect to theta is going to be cosine squared minus sine squared theta equals, and that's just a double angle formula, which is cosine 2 theta, which is going to be equal to 0 when we, So this is what we want to be equal to 0. Here's the derivative. We're going to set it equal to 0. So that tells us the 2 thetas where that derivative is going to be equal to 0, and that's pi over 4 and 3 pi over 4. That's where cosine is equal to 0. Double angle. So we got to be careful with this 2 theta, right? Okay. Now we're going to do the same thing with dy. So dy, we're going to get, okay, so we got our 2 sine theta cosine theta, which is sine 2 theta. We want to set that equal to 0. We want to solve this, and that's going to happen at 0 and pi over 2. Not pi, because remember, we got this double angle feature here. So the graph has vertical tangent lines at radical 2 over 2 pi over 4 and radical 2 over 2 3 pi over 4. Those are going to be our vertical tangent lines. And it's going to have horizontal tangent lines at 0, 0, and 1 and pi over 2. Now keep in mind, the derivative with respect to x being set equal to 0, that's what's going to yield our vertical tangent lines. Okay, and then our derivative dy d theta, so we're doing our derivative with respect to theta again, but this time in the y variable. So the change there, we want to set that equal to 0, so there's no change in the y. Does that make sense? I hope that makes sense. So here we're dealing with no change in x. Here we're doing with no change in y. So if there's no change in x, then that means it's going to be a vertical line. If there's no change in y, that makes it a horizontal line. And so we can see there's 4 total, 2 horizontal and 2 vertical. Theorem 9.10 has an important consequence. If the graph of r equals f theta passes through the pole, then theta equals alpha, and f prime of alpha doesn't equal to 0, then the formula simplifies to tangent alpha. So if it passes through the origin, then the derivative is much easier to do. It's just the tangent of alpha. So the line theta equals alpha is the tangent to the graph at the pole 0, alpha. So tangent line at the pole. So this is at the pole. If f of alpha is equal to 0 and f prime of alpha doesn't equal 0, then the line theta equals alpha is the tangent line of the pole to the graph r equals f theta. The next 2 slides in the presentation are just some common polar graphs. I'm not going to go over those. There's a limicon. Here's some more. Here's the rose curve. This one kind of comes up quite a bit. That looks like the infinity symbol. Of course, and then we got circles. Those are pretty simple to see. All right, so let's go ahead and move on to area of a region. So now we're in polar coordinates. So our formulas for integration are going to be a little bit different here. So if I'm trying to find the area of this, if you will, this slice of pie, how are we going to do that? So in the circle to the right, notice that the area of a circle, the sector, is as follows, and this is in polar coordinates. And so it's 1/2 theta r squared. So we're talking about, pi r squared. But here we've got 1/2 theta r squared. So the r squared kind of makes sense. But remember, now we're talking about pi. So pi is half of a full rotation. So it's 1/2 theta r squared. So if we consider the function r equals f theta, where f is continuous and not non-negative on the interval alpha to beta, then the region by the graph and the radial lines theta equals alpha and theta equals beta is shown here. So if we want to try to find the area of this region using integration, well, we're just going to divide that up into partitions, and we're going to integrate. If you want to think about it this way, we're kind of like doing, we're doing like we used to do rectangles in rectangular coordinate system. Now we're cutting little pieces of the circle, the pi. So that's that 1/2 theta r squared. Anyways, I'm going to kind of jump to the point here. This is a very important theorem. This is how you find the area in polar coordinates. So the formula is area equals 1/2 alpha to beta theta alpha, f theta quantity squared d theta. So that kind of looks very similar to what we've done in the past, but notice that there's no pi involved here. Okay, there's no pi involved here. Let's see an example. Find the area of one petal of the rose curve, r equals 3 cosine 3 theta. So let's look at a picture here. So this is the rose curve in this particular problem. There are 3 petals. So it's a good idea for you to graph this with your graphing calculator. I'm going to get the graph in here. You can see that the petal on the right is traced as theta increases from negative pi over 6 to pi over 6. So this dashed line here, the negative sloped one is negative pi over 6, and then the positive, so that one goes to pi over 6. So our area will be calculated by 1/2 the integral from alpha to beta of r squared d theta. So that's 1/2 negative pi over 6 to pi over 6 of our function in terms of theta, which is 3 cosine 3 theta squared. So now what we're going to do here is we are going to use so we're going to square this thing, and after you square the function on the inside, now notice that this 1/2 is changing, so there's going to be a factor of 9 that's going to come out of here because 3 squared is 9, so that's where that 9 came from. Then when we simplify this, we get the following. Now notice carefully, the angle has now doubled, so it went from cosine 3 theta to cosine 6 theta. So those are some trigonometric formulas or trigonometric identities. And so you're going to get 9 over 4 and then theta plus sine 6 theta divided by 6. We're going to evaluate from pi over 6 to negative pi over 6. And you're going to get the following answer, 3 pi over 4. Now, I'm just telling you, of course, you could use your calculator to get this approximation very quickly. And by the way, you could actually do this integral in rectangular coordinates. You would not have to be in polar form, and it will work out just fine. If you had to do this on the non-calculator portion, though, you would definitely be hard-pressed if you had to try to remember some of those trig formulas if you're not familiar with them. Okay, so next thing we need to look at is the intersection points on a polar graph. So where do these two polar equations intersect? Well, let's see here. If we look at this graph, we've got 2 graphs. We've got r equals 1 minus 2 cosine theta and r equals 1. So r equals 1, of course, is a circle. And then the r equals 1 minus 2 cosine theta, that is what we call limicon. And we want to find where those guys intersect. So as with rectangular equations, you can attempt to find the points of intersection by solving the 2 equations. So we can set those 2 equal, and we'll find out that they intersect at pi over 2 and 3 pi over 2. So once we've got those thetas, we could go back and find our r's, which have to be 1 because that's what the radius of the circle is. We have a problem here. You'll notice that the third point of intersection, this guy over here, was not found. We found 1 pi over 2 and 1 3 pi over 2, which are these 2 points. Why didn't the third one show up? Well, the reason the third point was not found, it did not occur within the same coordinates in the two graphs. On the graph of r equals 1, the point occurred with the coordinates 1 pi. But on the graph of r equals 1 minus 2 cosine theta, the point occurs on the coordinates negative 1, 0. So let's go ahead and look at our final example here. I think this is our final example, example 5. Let's find the area between two curves. And by the way, that's why we want to be able to determine those points of intersection, because if you have to find area between curves, you have to figure out what their intersections are. So I've got two curves. I've got a circle again. So this is r equals negative 6 cosine theta. And then we got a cardioid, which is r equals 2 minus 2 cosine theta. So here's the graph of this. So we are trying to find the area that these two curves have in common. So because both curves are symmetric with the x-axis, you can work with the upper half of the plane. Okay, so we're going to only look at the upper half. Now the regions that we have to find where these two guys intersect, we've got to find this region here, this pink region. We also got to find this area, this blue region. And then once we get those two areas, of course, we got to add them together, and then of course we got to double them. So the whole area we're looking for here is this whole area where these two graphs intersect. So the blue shaded region lies between the circle and the radial line 2 pi over 3. So that's this line right here. We're talking now specifically about this blue region here. Because the circle has a coordinate 0, pi over 2 at the pole, you can integrate between pi over 2 and 2 pi over 3 to obtain the area of this region. The region that is shaded in red is bounded by the radial line 2 pi over 3, and of course theta equals pi. So you can find the area of this second region by integrating from 2 pi over 3 to pi. The sum of these two integrals is going to give us the entire area that lies above the radial line pi equals, or theta equals pi. So here is the area of the blue region. So here's the blue region, and then here's the red region. So notice we're using our formula again. By the way, notice our total area, this divided by 2, that's because we're just finding the upper area. So this is going to be 1/2. We're going to go from pi over 2 to 2 pi over 3 of negative 6 cosine theta squared d theta. And then the second piece is going to be 1/2, 2 pi over 3 to pi of 2 minus 2 cosine theta squared d theta. We can go ahead and work these out. You'll notice that there's some simplification going on here. We're going to evaluate each of our antiderivatives. We get this hot mess of numbers. And so we get 5 pi over 2. Don't forget, though, remember our original area formula that we wrote there was a over 2. So now we need to multiply both sides by 2. So that gives us our final answer of 5 pi. The area between those two regions is 5 pi. We can check to see if that's reasonable. And indeed it is. Oh, I forgot. I did have one more thing. Arc length. Hopefully you guys remember our arc length formula. Here is our arc length formula in polar coordinates. It is alpha to beta of the square root of r squared plus dr d theta squared d theta. Now, if you remember that when we did these in rectangular, that was just a 1. And here's a quick, easy example of that. Here's our function in polar coordinates. So the arc length, we're going to use our formula. is going to be 0 to 2 pi because we're going all the way around the circle here. We're going to plug in our 2 minus 2 cosine theta in for the function, and then its derivative is 2 sine theta. And so we get the 2 radical 2, 0, 2 pi of the square root of 1 minus cosine theta d theta. We can integrate this using a trigonometric identity. Cleaning it up some more because that's inside there is a perfect square. But notice the square root of 2 would pull out, which would make that the front coefficient 4. This now has a nice integral of negative cosine theta over 2. We're going from 0 to 2 pi. And so we get our answer, which is 16. So the area of this inside of this curve, this parametric curve, or I'm sorry, polar curve is 16. And that will be that.